Okay, welcome back everyone. So today we are learning about the derivation. As I said in the previous class, I have written three important equations. In that one, I will derive one of the equation, that is instantaneous planar source. Diffusion equation for the instantaneous planar source. Planar source. Its solution of differential equation, diffusion equation and its applications. To derive this equation, we are considering the continuity equation of first order. In time and second order in distance. Distance x. Then the continuity equation is given as dou c t equal to d into dou c square into dou x square, where d is a constant. Okay. Instantaneous planar source is good example for this one is in industries of a semiconductors, the dopants are used this type of a phenomena, where we are considering the substrate material A and we are making a thin layer on the surface of B. Consider a small section of delta that is initially it is x equal to 0, here it is, and here it is x equal to infinity. Initially the silicon is a dopant only in the surfaces and assumed to be a negligible thickness. The whole assembly is heated such that the dopant starts to diffuse inside the material. It is important to control the diffusion dopant, the particular depth. So we will heating the substance and it controls the diffusion distance. And the next, the initial condition. Initially, there is no dopant on the surface of A. That means the initial concentration, the concentration of B is 0. Initially, we assume that thickness of layer is 0. Then x comma 0 is equal to 0, and we are saying that at after time t, the concentration of an dopant at the another surface of the substrate is also 0. It won't be, that means it won't diffuses throughout the sample, it diffuses on the surfaces. This is initially equation 1. And this is equation 2, and this is equation 3. The quantity deposited per unit time is given by delta. Deposited per unit area is delta. Then we can write it as integration from 0 to infinity c into dx equal to delta. Equation 4. We are integrating the equation 1. 0 to infinity e raised to kt dou c into dou t into dt is equals to d into integration from 0 to infinity e raised to minus kt dot square into dt. Considering the LHS side, this one. Zero to infinity e raised to kt dou t into dt. By integrating by parts, we will get as u into u is equals to e to the power of kt, and dv equal to, we are considering dou c into dou t into dt. Then differentiating this one, du is equals to minus k e to the power of kt into dt, and integrating this one, v is equals to c. Then the applying here, we will get it as e raised to kt into c 0 to infinity plus k into integration from 0 to infinity e raised to kt into t c c bar into dt. So applying the boundary condition, we can get it as 0 minus co x comma 0 plus k into c. Then the LHS is equals to k into c. Then consider the RHS. RHS, that is d into integration of 0 to infinity e raised to kt x square dt. Then we can take inside this one, can write it as 0 to infinity square e kt into c into dt. So then we can write it as d square. This is the RHS side. So we are considering, we are making the ordinary differential equation. So what's the reason behind this one? The reason is we are considering concentration is only the function of time, and only the function of position, not a function of time. That's why we are writing the ordinary differential equation from the partial differential equation. Okay. Yes. Now we can write LHS and RHS. Equal to RHS. Then we can write it as k into c bar equal to d into dou c bar into dou x square. This can be written as x square minus k by d c bar equal to 0. Okay. By solving this differential equation, there's a general solution for can be written as c bar equal to e to the power of lambda into x. Then we can write it as lambda square e lambda x minus k by d e lambda x equals to 0. That means lambda is equals to plus or minus root k by d. And then we have two solutions for this one. That is c bar equal to exponential of kd into x and c bar exponential of root kd divided by x. C bar equal to p plus p into exponential of minus kd into x plus q into exponential of root kd by x. Then from here the q is equals to 0. Then we can write it as c bar equal to p into exponential of minus kd by x. Okay, to find the values of p, we have to use the second boundary conditions. Values of p, we need to use second boundary conditions. Then we can write it as 0 to infinity c into dx equal to delta. That is, we can from here so we have used the second boundary conditions, and by integrating zero to infinity and 0 to infinity e to the power of minus kt c into dx into dt equal to delta into 0 to infinity e raised to kt into dt. Okay, sorry, I have to add one more tab here so that I can explain and derive the completely. Zero to infinity e raised to kt into c into dt. This is dx equal to minus delta by k 1 0 minus 1, that is equals to delta by k. Then from here we can conclude that 0 to infinity c bar into dx equal to delta by k. We know that therefore the c bar we know as p into exponential of minus root k into d into x. Okay, so after substituting here we can get it as p into integration from 0 to infinity exponential minus root kd into x into dx equal to delta by k. So after integrating and substituting the values, we can get the p value is equals to delta by root kd. So then substituting this p value here in the above equation shown here, that is c bar is equals to delta by root kd exponential of minus k divided by d. This is under root into x. Then this is Laplace inverse I am applying here. Delta by root kd exponential minus kd divided to x here. After Laplace inverse transformation, so we can get it as c of x comma t written as delta divided by root kd into t exponential of minus x square divided by 4d into t. This is the equation that we have written in the last class. It's a very important equation. So this is a complete derivation of semi-infinite plate. It's mainly used in the semiconductor industries for the diffusing things, diffusing the dopants. Okay, thank you.